So what is a geodesic? Let us first understand this. Just like any other mathematical concept and terms, they come from either Latin or Greek words. Geodesics actually come from the Greek word geodesia, which means division of the earth, and geo actually we know it means earth or ground, and deskein actually is another Greek word which means to divide or to measure. So overall what we can understand is that this term geodesy is a kind of a science which is involved of measuring the earth's shape and what are the distance that it covers over the surface. Now a geodesic in the natural sense is just a straight line either in a curved space-time or in a flat space-time. If we consider this to be a flat space-time and we take two black dots as 2 points, then what we can see is that the shortest distance between 2 points is a straight line. However, when we take the Earth's surface, a kind of a spherical shape, we find that the shortest path is not a straight line, but rather what is called a great circle of the Earth. Now, from here, what we can deduce is that a geodesic is nature's way of showing the straightest possible path which follows in a curved world or in a curved space-time. So it comes from the Greek words and it actually means related to measuring Earth's shape and distances. In straight line, it is the shortest path, the straight between 2 points, and in a kind of a sphere, it is the great circle arc. Now here is a point which I would like to make a note to all the students learning geodesic is that most of the students I have seen that they compare and they find that well geodesic is something which is very centralized or related to differential geometry which relates to general theory of relativity of Einstein. But the fact is not that. Now the word geodesic comes from differential geometry which is a branch of mathematics which I specialize and teach on curved space surfaces and we use calculus. So just a note of caution, as you can see I've taken a few snapshots from the table of contents of these two very good books. One is Andrew Presley's book, another by Thomas Bancroft and Stephen Lovelet. Now it actually shows that differential geometry teaches you geodesics. So it has nothing to do in particular with general relativity, although general relativity uses geodesic equation, but geodesic equation is taught on every part of differential geometry on an elementary level or on an advanced level. So this is a point that it is a part of learning and understanding differential geometry. Now we go ahead and understand what is called the geodesic equation. Now when we talk of the geodesic equation, as I told you that it actually describes the extremal path between 2 points in a curved manifold which is derived purely from geometry. Now there are different formats, different indexes which comes when you are learning geodesics. So some looks like this, some looks like this, just the nu and the lambda etc. changes, but we will look in this first part. This part which is more or less a kind of a taken for granted a good convention. Now as you can see again a point is that this has nothing to do with relativity. This is just a differential geometry, purely geometric equation. Now first of all I would like to define what this S is in the denominator which is repeated on the left hand side, on the right hand side. So S I would say is a kind which is called an affine parameter. I will just explain you what this affine parameter means. So the word affine actually comes from the Latin words. In English we say that we have an affinity towards this, that. So it is means related. It can mean connected, it can be mean bound together. So I have an affinity towards my friendship, I have an affinity towards vegetarian food. So it means related or connected to something. So this is the meaning of the parameter, the word affinity. So as you can see that the word affine is something which is related to, linked or proportional to. So in mathematics also affines or affine connection, affine parameter etc. means transformations or structures that actually preserves the straightness or parallelism but not necessary distances or angles. So what is an affine parameter? In simple words, we can say it is basically a ruler you use to march along a curve. So it doesn't matter what units you use as long as they increase uniformly along the path. So each point on the curve is tagged with a value of this parameter, which we call as the affine parameter. Let me give you a visual example which will make the concept of affine much more clear. So for example, if you're walking along a straight road, you can mark your position by distances in meters, and that can be called as an affine parameter. You can also use time if you walk at a constant speed, also an affine parameter. Now, as you move along a great circle, you would measure the progress by arc length, that is the distance traveled. Or if you move at a constant speed, your wristwatch time could be used instead. So from here, what we can say that both are affine parameters, just these are two different rulers. So arc length is an affine parameter for a great circle, which can be used in a Riemannian manifold. So from this equation, we have already understood what is S. That is an affine parameter, which is a kind of a ruler which we use to measure the distances. Next, we look in this one, x raised to the power p, or we can say in simple words, it means the pth coordinate function. So S again is the affine parameter, and x to the power raised to the power p are coordinate functions of the curve of the geodesic. Now this S we can call mathematically something looks like this. That means this S maps to x0, x1 and so on. So from here what we can tell is that we take a parameter which is S, the affine parameter, and it tells where you are as you move along the curve in space-time. Now let me give you a visual example which will make things even more clearer to you. Now here you can see this is a curve, and I have taken a parameter, for example this S, and I move along this. So it curves, it takes this shape and it comes over here. Again, if I go back, it takes the same animation, it takes the shape and it moves. So what is happening over here? So I have taken S is like a label or a time parameter that actually moves along this curved path which you have seen. So if I now define the parameters x mu as x0, x1, x2, it means that it gives the coordinate where you are either at x0 point or x1 point. Similarly, I can take x1, x2, x3 and so on. It also gives the coordinate of the parameter. Now if I combine these two equations, that means x mu and x1, we get something like this. What it tells? It tells nothing. It tells that the position of a particle or an observer where it is in a space-time at that moment which is labeled by S. Now you might be wondering, now if I go back to the earlier part, here you can see that there is an xp. However, when I move along the curve here, we are trying to define something as xp of S. So why it is so? So in order to avoid cluttering, which takes a long time everywhere to write xp of s, xp of s, it makes the equation looks heavier. So we avoid this and we just write as xp. So this is something which you can find similarity to ordinary mechanics, that d square x by dt squared is equal to f of m. Right? So T in mechanics we can say is the affine parameter of S in relativity. Do we repeat the T? Well, we don't. So T in mechanics is something which is similar to affine parameter of S in relativity, and X of T in mechanics is something similar to X of P of S in geodesic. So that is why we don't write X of P of S, x raised to the power P of S, but rather that XP. So we assume that it is to be known. So from here now we move to the geodesic equation where we are trying to understand this part, d square xp upon ds square. Now this is obviously, you can understand very well, this is nothing but the second order derivative. So this is the second order derivative of the coordinate xp with respect to the parameter s. So this is the second derivative of the coordinate xp with respect to s. Intuitively you can think that this is a coordinate acceleration. That means how fast the velocity coordinate xp dxp by dxs ds changes. So in flat Cartesian coordinates for a straight line, this term alone actually means 0 in terms of constant velocity. So I have told you the intuition. Okay, what is this x raised to the power I of s? So what it actually means is that the ith coordinate of the geodesic curve. You have already seen that how the affine parameter s moves. So x of I is the ith coordinate of the geodesic curve. That means it depends on the parameter s. So I am highlighting this. That means I am trying to explain this part. Okay, I am again going back. So this is the ith parameter of the coordinate of the geodesic curves. It depends on the parameter s, and this is the area which I am trying to define. So here what we can say, dxi upon dxs, this is the rate of change of that coordinate along the curve. Remember that ds here means differentiating with respect to the parameter s, and let us not confuse it with the line element of the metric tensor ds. No. This is a point of confusion. The denominator here means differentiating with respect to the affine parameter s. It does not mean that it is the line element of the metric tensor. So dxi upon ds actually means differentiating with respect to the parameter s. It is exactly, okay, so fine, let us go. It is exactly like in mechanics when you write dx upon dt, where you are differentiating position xt with respect to time t. So that's it. So now if I say this, that because it depends on the coordinate system you choose, not on something absolute, what I'm trying to mean is this. I'm trying to mean that the quantities like dxi upon dx and d square xp upon ds square, both the terms shown in the geodesic equation are not absolute. That means physical properties that exist independently of how space is described, they depend on the mathematical coordinate system being used. So it depends on entirely the coordinate system, not on something absolute that you select. So again a note of caution here, the denominator ds means you are differentiating with respect to the affine parameter s. xi is the ith coordinate of the geodesic curve. It depends on the affine parameter s. So xis is just like a function, position as a function of parameter. Fine. So as I was talking that this is a very confusing thing, that please do not get confused with the line element ds, because in differential geometry or general relativity, the line element is defined by this metric tensor. Here actually ds is meaning that there is a small distance measured along the arc or along the curve, proper time in relativity. It comes directly from the metric tensor. Now, you might have a question that why it does not explicitly involve line element. The reason is that the geodesic equation is all about coordinates. So we tell that using calculus, that means we are using local coordinates which evolves as you move along a curve. It is a differential equation for the curve, that means second derivative plus the curvature terms, and all it needs is nothing but a parameter along the curve, the affine parameter s, and the Christoffel symbols, which themselves are built up from the metric. So remember this thing very important, that the line element ds square, which you can see in the metric tensor, is used when you want to measure lengths or times along a curve. For example, computing proper time for a world line. For example, computing distance on a sphere. But the geodesic equation itself is about the shape of the path itself. So from here what we can summarize is that the line element ds square is about measurement of line length and time. The geodesic equation is about the dynamics of the curve, and they are connected because the geodesic equation is derived from extremizing the line element, but once you have the equation ds square does not appear explicitly. So this is a point of note to give you an idea that this ds and the line element of ds are not the same. So from here, if you again revisit the geodesic equation, we find both of these actually means the same. What does it mean? That means that they are the components of the tangent vector to the curve, that is, or the velocity vector if you think physically. So the only difference that you have got is the index, which tells you which coordinate you are looking at. Let me give a very simple example. In 3 dimension, if we take a curve as xs, ys and zs, then by differentiating we get a value something like this. So the tangent vector will look like this. So here, from here we can infer that dxi by ds and dxj by ds are entries of the same vector. Nothing great or extraordinary to think about at this moment. So this is what the left hand side and the right hand side of the geodesic equation looks like. Now we come to the central part of understanding the Christoffel symbols, and this is actually defined by Elvin Bruno Christoffel, and it has been dedicated by his name. So first of all, what are Christoffel symbols? Before that, I would like to give you an analogy. This is a very common thing. This is the grid. And think of the grid as it is a coordinate system drawn on a flat space. And on flat space, as you can see, these coordinates are straight and uniform. This line and this line. These boxes and these boxes and these boxes. So you can see that they are straight and uniform. And if you move along them, there is nothing that you need to correct or nothing extraordinary happens. Now I take this one where I put a heavy mass, for example, this earth. You put a heavy mass, and now you see, if I consider walking straight, the numbers of the grid of the coordinates that describe also changes. So here you can see this box will change here. You see that it has stretched, and it has further stretched over here. So when you put a heavy mass, the space is curved. Even if you try to move straight, as you am trying to move here straight, I won't be able to do. So along your old coordinate lines, your path subtly bends because the space itself is distorted. And here the Christoffel symbols come in play. So what the Christoffel symbols do is that they tells you exactly how the coordinates are bending or changing at each point. So remember, this is not a tensor component. They are not curvature themselves. They are like a correction factor. They correct you and they tell you that how the direction of your axis is changing as you move. We will explore these indices further in our video. So this is a fairly kind of an intuitive and a schematic diagram which gives you an understanding that how things bend and why the Christoffel symbols are required. So here you can see further that this is the Christoffel symbol. The gamma is basically the Christoffel symbol. The top index, we will see further, is how it tells you in which direction the new component of the vector points, and the lower indices actually tells how you moved in the coordinate directions. This is a kind of a schematic diagram. Let us zoom in this, we will understand. So the grid lines actually represent the system. On flat space, they would be straight and uniform. In this image, you can see the grid bending around the hill. So that bending is exactly what Christoffel symbols measure. And the hill is the elevated point, represents a mass curving space. Further, you can see the arrows show how geodesic, straight path geodesic in curved space would change. So without the bump, the arrows will be fairly straight. The fact that the curve or bend is what the Christoffel symbols accounts in equation. And the person standing on the top, you can think that as an object moving through curved space. If I zoom further in this illustration, then what I guess is that the grid boxes are distorted near the hill. This tells us how the metric, the metric changes, and the grid lines are bent instead of staying straight, and this is where the Christoffel symbols come in. So the extra term, the capital gamma, accounts for the stretching and bending of the grid, and this one tells actually that are not curvature themselves, but they describe how the coordinate grid stretches. So the Christoffel symbol tells how the local slope corrections, I would say it would tell you how the local slope corrections you would need in order to stay on a straight path according to the curved surface. So if you stay on a straight path, what would be the local slope correction? And that correction would be in terms of the curved surface, how things will move. This is a pretty hand-wavy and a very basic, intuitive, illustrative example of what Christoffel symbol actually does. Now, in order to know a little bit more about Christoffel symbols, we have to go a little bit more in this part of our video, where I would like to explain a very important concept, which is called how basis vector changes in a curved manifold, or you can say in a curved surface. Now, I know that you all know what is a basis vector. This is very, very rudimentary and elementary in terms of understanding. So this is an illustration of an basis vector. So as you can see, the vector A in 3 dimension is just a linear combination of the standard basis I, J and K. So for example, in R2, we get a basis vector as this, and in R3, we get a basis vector something as this. What is important is that here the basis vector doesn't change. So geometrically we can say Christoffel symbols are interpreted as tools which will tell you how basis vectors change in a given coordinate system. That means the basis vector can change due to curves, due to geometry, etc., and the Christoffel symbols describe both of this. That means how the basic vector changes due to the coordinate system through a curvilinear or due to the geometry of space itself. First of all, I would like to give you an example, very simple example of the change of basis vectors in terms of polar coordinates. You all know what are polar coordinates in 2 dimension. This is a polar coordinate, and straight away from this illustration you can see what happens. This E theta or E theta is the length of the basis vector, and it increases as you move away from the origin of the polar coordinate. So here are a few important things. The black grid, the polar coordinate system R theta. Red arrows, basic vectors which are ER and E theta. Key points is that the length of the E theta basis increases with R. Why? Because moving a small change of delta theta sweeps across a larger arc, which is delta is equals to R delta theta. So the unit step in the theta direction gets longer and longer with the distance from the center. So this diagram actually shows that the coordinate grid itself is stretching and twisting. So as you can see, as you move outwards toward the tangential E theta also stretches. So since the basis vectors here themselves change with their position, if it changes, then what happens? Their derivatives will not be 0. So from here what we can say that in polar coordinates, because the basis vector themselves change with the angle theta, so when you differentiate you get new terms, and that makes things very interesting. So in Cartesian coordinates, as you have seen, I and j are fixed, both direction and magnitude. In polar coordinates, ER keeps the same length but rotates as theta changes, and E theta not only changes, rotates, but also changes the length as R changes. So here I would like to show a very simple example which will make things clear. I'm going to take the same polar coordinate. So we know that in 2-dimensional polar units are calculated as I and j. Now if I take ER, it would be this. If I take E theta, it would be this. So ER means it is pointing straight away from the center, and E theta means pointing along the direction of the rotation, that is the tangent. Fair enough, till now there is no problem. Now if you try to differentiate with respect of theta, you see what happens. We get a value of E theta and minus ER. This is something important, this one which I just highlighted in red. So what does it tell? This tells that the derivatives are not 0. What does it mean the derivatives are not 0? That means as you rotate, you can think of as a merry-go-round. As you rotate, the theta changes and ER rotates towards the E theta. Similarly, E theta rotates towards minus ER. And this is typically that by differentiating, when we are not getting a 0 value, that means the basis vectors are changing. So that means in Christoffel notation we can say gamma theta R theta equals to 1, the value, and gamma R theta theta equals to minus 1. So here you can see now that I will tell you that this one ER, your straight out direction changes, and E theta, your rotation direction also changes. So that means understand from here that Christoffel symbols have nothing to do typically with geodesic equation. You can find out a Christoffel symbol of polar coordinate, spherical coordinate, whatever on a curved surface. So this actually shows that what it means by differentiating they are not 0, that means the basis vectors are changing. Let me give you another very simple but a very important example of how basis vector changes in curved manifold. Now I want you to imagine, say for example, we have some curved coordinate, this one, with the coordinate axis x1 and x2. I can see x1 which is in green and x2 on the top which is in blue. And with the basis vectors in this direction E1 and E2. Now with the first one, now you see when we the next picture, the next one where you can imagine along the x1 axis, you can see how the basis vector E2 changes along with the axis x1. So now I can tell that this E2 which changes, you can see the E2 changes, the blue one how it changes. So if I now take this E2 the basis vector, how it changes, what I can do is that a small change in a vector along its coordinate axis is simply the partial derivative with respect to that particular coordinate. So here what I am drawing is this red line is basically the difference. So change in the basis vector of E2, the blue one, along the coordinate axis x1, the green one, is basically given by this. Partial of E2, that means the basis vector, with respect to partial of x1, that is the coordinate x1. Very simple. Now, this red vector can also be extended and divided into components. How? Very simple. I take the red vector, which is already the same, partial E2 by partial x1, and I take the green one. And what I do is that I put a dot product, because it is just a projection of one, and I write the Christoffel symbols. So gamma with 1 on the top. Why 1 on the top? Because this E1 is the green one. And what I am differentiating? I am differentiating E2 with respect to x1. So that is why in the denominator we have 2 and 1. Now if I take the blue one, you see that again partial E2 and partial x1 remains the same, but I put a dot product of E2. And the gamma changes. Why? Because now I am not differentiating E1. I am differentiating e raised to the power 2. So the Christoffel symbol will have a 2 on the top. And what are the numerator, denominator? 2 and 1. So it remains the same. So this is a pretty good example how the basis vector changes in curved manifolds or in a curved surface. I will like to show you another example, which so here it is the E1, the green one, and it is the E2, which is the blue. So I have taken just the same color conventions in the partial differential part so that it makes things easier to understand. So from here what we can say that we have already seen the polar coordinates. It is all done, isn't it? We have just seen this one. Now I would like to show you how the basis vector changes in a spherical coordinate. Very simple. In Cartesian coordinates, what we do, I, j and k are fixed everywhere. But in spherical coordinates, so this one is x, this one is y, and this one is z. Simple. Now here what will happen, that the spherical coordinates are labeled as er, e theta and e phi. And these are drawn in red. So this part is the basis spherical units vectors. You can see here, I am again zooming so that things become clear. Er, e phi and e theta. So er, as you can see from here, points radially outwards from the origin. E theta points in the direction of increasing polar angle, and e phi points in the direction increasing of the azimuthal angle, which is the phi. So from here we can rotate e phi and e theta accordingly. So though these basis vectors depend on the position of that point, what we see is that if you move to a different location on the sphere, then ER will automatically change because it is radially pointing outwards in a different direction. So from here what we can say that unlike Cartesian bases, which are very fixed, EI, J and K, here the spherical basis vectors are not globally fixed and they change the orientation depending on the coordinate of that point. So this will make you clear and give you a clarity that why we need Christoffel symbols and how this E theta and E phi rotate accordingly, and the basis vector depends on the position on where you are on the spherical coordinate. A very important concept laid down, a change of basis vectors in spherical polar coordinates. There can be many other curved manifolds. Now we come to understand what are called the components of the Christoffel symbols. We have already seen this one, that it is basically how basis vectors change, and basis vectors may change due to certain reasons. Now I would like to explain what this means. This is the Christoffel symbol we have seen. So if I take this point, it will basically mean that the connection coefficient. So let us put it in very simple English words. This actually tells how the mueth basis vector, the denominator, the mueth basis vector twists or changes when moving along the nueth direction in the direction of E lambda. That is the right hand side. Again I am repeating. This actually tells how the mueth basis vector twists or changes when moving along the nueth direction in the direction of E lambda. So this is how we tell mu is the basis vector we are differentiating. Obviously Nu is with respect to which coordinate, and lambda is the component we project into. That is why we use a dot product, because dot product is basically a projection of the vector. So it is very simple to remember. Remember, the lower indices are mentioning what you are differentiating, and the upper indexes, or the index, is mentioning which direction the derivative points after you make the differentiation. So lower indices what, and upper index which direction you are. So let us take a further look in this part. So this entire E mu is basically the basis vector of the coordinate system. It depends where and how you are moving. This this part is actually telling the derivative of the basis vector with respect to the coordinate. As I told, muth basis vector changes as you move along the nuth coordinate direction. E raised to the power lambda, this actually tells the dual basis vectors. So it satisfies the Kronecker delta part, and its role is basically to pick out the coefficient of the derivative in the direction of the lambda-th basis vector. And the dot product, very simple, it is the projection, so it extracts the lambda-th component from the derivative of E mu. So what we can summarize from here, that you need to pick up a basis vector which is E mu. Then you see how it changes as you move along the x nuth derivative. Then project that change onto another basis vector E lambda, which you use as I would say the dot product, and the resulting number is equal to the Christoffel symbol, which is this lambda raised to the gamma raised to the power lambda, and at the lower indices is mu and nu. So this actually clears all the components of the Christoffel symbols. However, there is one concept which I will quickly touch base before we end this video. Now, when we talk that derivatives are not zero, there are derivatives which are zero. So consider a flat surface. I put on the projections, or I would put on the components of the basis vector. Here it is 0. So this happens for Cartesian coordinates are fixed, so I get I is equal to this, j is equal to this, and so on. So if I want to say the Christoffel symbol of a flat space, it will be equal to 0. So in flat space time with Cartesian coordinate, vectors actually don't rotate when you move, and differentiating a vector gives a simple, you only differentiate its components. So here you're differentiating only the components. Now where are the derivatives not 0? That is where the life becomes a little bit difficult. Here it is where that happens in a curved manifold, and we have already seen this, it is not 0. It is ER or E phi, etc. So here the Christoffel symbols are not 0. So what happens is this, the basis vectors themselves rotate when you move, as you have seen polar or spherical coordinates. Differentiating a vector actually gives you two parts, derivative of the components and derivative of the basis vectors. If you go just quickly to the first part of this video, here I have written at the bottom that differentiating is simple. Why? Because you only differentiate its components. But when I come to this part, you see there are two parts. The first part is the component, which is done for Cartesian coordinate, but derivative of the basis vectors and Christoffel symbols actually take part of the second part. That means it does all the correction terms of the differentiation of the basis vectors, and the ordinary Cartesian components does the I would say differentiation of only the components. So now it is a time to quickly summarize and find out the link between Christoffel symbols and geodesics. So we can say that Christoffel symbols are basically tells how the coordinate system itself is curving or changing. It is like a kind of a rule book, an instruction how vectors change. In flat space there is no problem, and in curved space we have seen sphere or polar coordinates, the basis vector themselves change direction, and Christoffel symbols describe how you change. In case of a geodesic equation, there is a part of Christoffel symbol, and a geodesic is the shortest path. So connection to the Christoffel symbol is that the geodesic equation uses Christoffel symbols in order to tell you how an object should move if no forces are acting, or just following the natural curve of that space. Now here I would like to tell you that I have actually avoided two concepts which I will explain in the next part of the video, which is called Levi-Civita connection, which I will talk about that later. So now you can see that this is the general geodesic equation, which is a geometric form which is taught in the ordinary courses of differential geometry, and this is the geodesic equation used by Einstein in general theory of relativity. Now there are a few questions which are still unaddressed. First is that why these equations have got equal to 0. What does that mean? Why there is a tau square and an s square? Do you find any kind of a similarity between this? Also there are 2 d taus at the denominator. All this I'm going to address in the next part of the geodesic equation. So that's all for today's video. Thank you very much for taking your time and watching this video. If you have liked, please do not forget to subscribe to my channel Physics for Students and click this bell icon ringing so that you get all the notification from Physics for Students. You can follow me on my social media handles, and you can write to me on my email ID, which I try to respond as early as possible. Physics for Students will be soon back with more interesting videos and continuing with the part 2 of the geodesic equation. See you soon in the next video, but till then, may the good Lord be with you.